We're going to have a look at the mechanisms that you need to learn now. And the one we're going to start off with is radical substitution, free radical substitution. Halogenation of alkanes. First of all, I'll go through the actual reaction that we're talking about. If we have methane and we add chlorine gas, we either need UV light or high temperature like 300 degrees Celsius in order for this to happen. And then you end up with chloromethane and HCl. So that's the overall reaction. And we're going to look at the individual steps of the mechanism. It starts off with the initiation step, and that's step 1. And that involves the homolytic fission of the chlorine bond, chlorine-chlorine bond, to produce 2 chlorine radicals. And that needs the UV light. It needs quite a lot of energy. So the chlorine-chlorine bond breaks by homolytic fission, producing 2 chlorine radicals. Now, radical is a species with an unpaired electron. And that's homolytic fission, because both the species end up the same. Now we'll move on to step 2, which is the propagation step. Now, in the propagation step, that's where the products are made of the reaction. So if we remind ourselves of the actual reaction itself, the overall reaction. So this isn't the propagation step, this is the overall reaction that I'm going to draw here. So I've got CH4 plus Cl2 goes to CH3Cl, chloromethane plus HCl. That's my overall reaction. So in this propagation step, we're going to make those products. We're going to make chloromethane and HCl. So in the propagation step, this is what happens. The chlorine radical reacts with the methane and produces a methyl radical, CH3, with a lone electron, and the HCl. And now that's the product that's formed overall. You see HCl. So that's the first reaction in the propagation. The second reaction in the propagation step will start off with the methyl radical, CH3, with an unpaired electron, reacting with chlorine gas, Cl2, and you end up with chloromethane and another chlorine radical. So the chloromethane here is what's produced as a product. So we've produced our 2 products. You also produce radicals. Whenever you do a propagation, you generate more radicals. Now the step 3 is the termination, and that's an easy one to work out because it's where all the radicals that you've generated can come together. So far we've produced methyl radicals, chlorine radicals, and they can come together in different ways, as we'll see. So 2 chlorine radicals can come together and just make a chlorine molecule. Alternatively, we could have 2 methyl radicals coming together, and that will make ethane, CH3CH3. Or we could get a methyl radical and a chlorine radical coming together, and that will make more chloromethane. So those are the 3 termination reactions. Something that's important to bear in mind when you talk about free radical substitution is that radicals are very unpredictable. Radical reactions are very unpredictable. And you can produce lots and lots of different products. And we'll just go through how that's possible. You could end up with dichloromethane because the chloromethane could then react with the chlorine to produce dichloromethane. You could produce trichloromethane and even tetrachloromethane. Also, as we've seen, you can generate ethane, and the ethane itself can undergo halogenation and form chloroethane. Now we're going to have a look at another mechanism. This is for electrophilic addition. This is the reaction that the alkenes undergo when something adds onto the double bond very often. So we'll start off with ethene and bromine. Now bromine in this case is acting as the electrophile, and the bromine adds on to the double bond and you end up with 1,2-dibromoethane. Now the mechanism to that is on another video. It's on YouTube and it's an animated one, so I'm not going to dwell on that. So I'll move on now to another mechanism. We're going to look at nucleophilic substitution reactions, and we're going to have a look at the reactions of halogenoalkanes, the hydrolysis of halogenoalkanes. That's what we're going to look at. And we'll start off with the halogenoalkane. I've got 4 carbons there, and on the end carbon I've put a halogen iodine, so it will form 1-iodobutane, 4 carbons butane. I'm reacting that with KOH, potassium hydroxide, reflux it, and as a product we're going to end up with butan-1-ol, because what happens is the OH from the hydroxide replaces the iodine. It's just a straightforward swap over, in other words a substitution, straightforward substitution, butan-1-ol. Let's go through the mechanism for this. Now when you're doing this, what you need to do is to change your halogenoalkane into a 3-dimensional tetrahedral-like arrangement. So you start off with a carbon with the tetrahedral bonds drawn with the wedgie diagram, and you'll put the halogenoalkane on the bond that's furthest to the right there. Now I can put my 2 hydrogens. Those 2 hydrogens there represent those 2 hydrogens there. The long chain alkane we can put all together on one of the bonds. So it'll be CH2, CH2, CH3. That's that structural formula up there converted into a tetrahedral type 3D type arrangement. You can see that group there, look, I've highlighted is that group. The hydrogens, let's have a look at those as well. Those hydrogens there represent those hydrogens, and obviously the iodine is like that. So what I'm showing there is how to change that structural formula into like a 3D arrangement. Then we only need to worry about the OH, because the potassium's a spectator ion, it doesn't actually get involved. So we start with the OH, and we've got the 2 lone pair. We've got the lone pair of electrons on the OH. Not forgetting to put the dipole on, that's important. The iodine's more electronegative than the carbon, so there's a dipole there. Now the lone pair of electrons from the OH is attracted to the electron deficient carbon. And the iodine carbon bond that breaks by heterolytic fission. Both electrons go to the iodine. So we draw the structure again. This time we do it the other way, like a mirror image of it. So we still have the same wedgie diagrams, but we put them facing the other way, because it's like an umbrella turning inside out. And then we put the OH on the other side, and it loses the iodine. Now in this case, the OH minus, the hydroxide ion, is acting as the nucleophile, because it is donating the electron pair to form the bond.